Sanket, am I audible?
Yes, sir.
Are you able to see the screen?
Yes, I can see it.
Now, we're coming to the next class of flat-plate collector. So here we will discuss about the transmissivity and absorptivity. Just a minute. Hello. Yes. Any connectivity problem is there? Sanket?
No, sir. No, sir.
Okay, thank you. Okay, now coming to the next part. So before analyzing the flat-plate collector, first we have to observe the parts of the flat-plate collector. So with these parts of the flat-plate collector, one can understand how the transmissivity or absorptivity of the different mediums can be analyzed, and also the heat transfer analysis can be done using this flat-plate collector, and how it is working on the greenhouse effect. So as I think many of you have heard in atmosphere, also we call it as a greenhouse effect for the plantation and other things. So here coming to the working of the flat-plate collector, we have a metallic plate here. This is the absorber plate. We call it as absorber plate, which is made up of metallic plate. Okay, with this metallic plate, we are going to attach many number of tubes, or the sheet metal itself is molded in the form of tubes and flat plate. This flat plate is focusing or facing towards the sunlight or the light which is passing through the covers. And these tubes will be running with fluid. So whatever the heat transfer or fluid is required, that is flowing through the tubes. It may be chemical, water, or any fluid which is for the tubes. So that fluid will be flowing through the tubes. And below this flat plate and tubes, we are going to use some insulating material. Okay, so insulating materials, earlier class I have given the examples like glass wool or mineral wool or asbestos powder. Many types of insulator materials are available. So that is kept at the bottom. And above this casing, so complete casing will be done as a box. And above this, one or two glass covers will be kept so that any dust particles falling on the absorber plate will be reduced. Also, the reflected radiations from the absorber plate can be reduced, which can go outside the glass covers. And these glass or plastic covers, which are transparent in nature, will be transferring the solar radiations. Okay, these transparent covers will be transferring the solar radiation inside this transparent plates. And what will happen is the short wavelengths, as we discussed in the solar spectrum, the very short wavelength radiations, which are invisible or infrared radiations or ultraviolet radiations, only in that range will be passing through these glass covers and will be reaching the absorber plate. And the one of the advantage of the interesting part is the reflected radiations from the absorber plate of the second glass cover plate. Here you can see the second glass cover plate will be reflected back with the larger wavelengths or the longer wavelengths. That will be reflected back to the absorber plate. That's the advantage. Although that is the interesting part. Similar to the atmosphere of the Earth itself, means whatever the absorber plate is shown here, that will be acting like a our Earth's surface, and these two glass covers and the space in between these two glass covers will be acting like the atmosphere. And top glass cover, you can assume it as a ozone layer. So this ozone layer and atmosphere are permeable to the short wavelengths of the visible range of light, and it is not losing or passing the long wavelengths. Means Earth is not losing any energy, or this absorber plate is not losing any energy, which is reflected back to the atmosphere of the glass covers. So that is one advantage where the re-reflected back radiations will be absorbed. This absorber plate, the temperature of the absorber plate can be increased. So this is the greenhouse effect where Earth as well as black plate collectors are going to absorb more energy by re-reflecting the longer wavelength radiations. So that is the one advantage of using these glass covers. And also, if you use the number of glass covers, the absorption will be high, but the transmission of the solar radiations will be less. We go for more glass covers. That's why minimum we go for 2 glass covers or 1 glass cover, so that transmission can be improved, reflections of the loss of energy from the backplate filter can be reduced. That is the phenomenon. Next, going to the other parts. So here, one of the concepts what you have to learn is before thermal analysis, the transmissivity and the absorptivity of the glass cover system. So here, coming to the first part, that is transmissivity of the cover system, we have to first understand what is the Snell's law. So I hope in physics subjects you have learned this Snell's law. That is, in given two mediums, say for example, medium 1 is atmosphere, medium 2 is after one of the glass cover or the glass cover itself. So there are two mediums, and solar radiation, which is the incident beam radiation, we given by IB, which is passing through the glass cover at an angle, or it may be at a zero angle depending on the given height. Now that angle of incidence is taken as theta 1, and the laws of reflectivity or refraction, if you see, the refracted radiation will bend towards the vertical line. So the theta 2 will be less than theta 1 as per the principle. And reflected radiation, that is IR, the beam radiation which is reflected back from the glass cover, if you see, it is in the same incident angle itself, theta 1 itself. So incident beam radiation and reflected radiation will be at theta 1, same angles. Refracted beam radiation through the glass medium will be theta 2, which is less than theta 1. And the interference, if you see, interface, it is the interface. So if you consider one glass cover, that medium 2 is the glass cover 1, and medium 1 is the atmosphere. So using this Snell's law and using the refractive index, that is N1 and N2 for the given mediums, refractive indexes, I can write N1 into sin theta 1, okay, in the medium 1, N1 into sin theta 1 is equal to N2 into sin theta 2. This is the Snell's law, through which one can find out the angle of incidence or angle of reflection or angle of refracted beam. All three angles can be found out. Or if you unknown the N1 and N2 or the refractive indexes of the given mediums are unknown, then one can find out N1 and N2. Okay, this is called as Snell's law. So next is finding this reflectivity. So that reflectivity of the given medium glass or plastic can be written as rho reflectivity. So for one glass cover, I can denote it by rho 1, or if only one is there, no need to represent it by rho 1 or rho 2. So simply I am writing rho because the medium 2 itself is having some reflectivity. Okay. So that reflectivity can be written as ratio of the reflected beam radiation to the incident beam radiation. That is IR divided by IPR. This ratio of both the radiations of reflected radiation and incident radiation will give us total reflectivity of the given medium 2. Okay. Now coming to the other parameters. Now here I have taken the example of glass cover system. So here one glass cover is considered, the glass cover with transmissivity tau. And what is this transmissivity? To understand this, We take one of the solar radiation or the beam radiation, that is the total radiation, which is including beam as well as diffuse radiation, which is passing through the glass. Now, once it passes through the glass cover, what will happen? Some of the energy will be absorbed by the glass. Okay, that's the absorptivity. It is written as alpha U. Green color alpha is written. That's the absorptivity. Some part of the energy is absorbed by the glass, and some part of the energy is transmitted. While transmitting, some energy will be lost. That energy lost, we are going to multiply with the transmissivity of that glass cover. So by this, if you multiply IT into transmissivity, I get solar flux or per unit area, what is the solar incident radiation without absorption. How much is transmitted, that I can multiply that transmissivity factor with the total radiation. And after absorption by the glass cover, see here, after absorption, what happens? Glass cover will heat up and some energy will be reflected. So similarly, if I take the radiation which is falling in the absorber tube, with that absorber tube, if I consider, what will happen here? At the bottom, solar flux absorbed by the absorber plate of the absorber glass cover, if you consider, I can multiply total beam radiation incident into transmittivity of the glass cover into absorptivity of the glass cover. So this radiation is falling on the absorber plate. I hope this point is clear. On the absorber plate, after the radiation passes through the glass cover, one of the glass cover to consider, it is going to reduce by some amount. What is that reduction? That reduction we are going to get by multiplying absorptivity of the given glass cover and the transmissivity value of the glass cover. So if you multiply all these three values, I will get what is the actual solar radiation or solar flux falling on the absorber plate in one radiation. Similarly, like this, multiple reflections will be taking place inside this glass cover, and small amount of energy will be lost to the atmosphere. As I told you, the Snell's law. So what will happen? Some of the energy will be reflected there, and due to this reflection with longer glass cover will not allow some of the longer wavelength energy. What will happen at this reflection time? What will happen? The reflected radiation is also lost the energy to the absorber plate also. So finally, the reflected radiation from the absorber plate is want to come down. Now I am going to multiply with this total radiation incident, loss of energy due to transmissivity. After absorber plate, I am going to multiply with 1 minus tau because of the absorber plate. And because of the absorber plate of the glass cover, both absorption, I am going to multiply with alpha. This is the reflected radiation which is going to be lost to the glass cover. Like this, the reflection, refraction, or the absorption phenomena is going to take place in the flat plate collector. So these are the three phenomena. Now to find out the transmittivity after absorption, tau alpha, if you want to find out that. So what we can do is we can take the ratio of this IL. IL is the reflected beam radiation. After diffraction or after the light passes through the medium, that radiation we are going to consider it as IL. In case of IT, if I multiply IT into I tau, I can take it as IL. IL by IB. Or you can see here in the Snell's law, reflected beam, I can consider it as IL. To the ratio of, to the in the denominator, I can consider total incident radiation IB. So that ratio will give us the transmissivity due to absorption. Is that clear? So similarly, I can write using the Snell's law also, other than this ratio, taking the ratio. If you know the Planck's constant of the extinction constant, we have given extinction constant K, so that is given by per meter, minus e raised to minus K into delta C. So here in this Planck's formula, delta C is thickness of the glass cover. If n number of glass covers are there, you can multiply K with n into K into delta C. If the radiations are falling with the normal, 0, or when the sun is at zenith. If the sun is giving the radiation certain inclinations, then I can write this equation. Tau alpha equal to e raised to minus n. N is the number of glass covers. Here only one is taken, that's why they have not denoted any number. It's like 1 because of the one glass cover. It is minus k into delta c divided by cos theta 2. So here cos theta 2 is nothing but the refracted beam radiation angle. Then the solar radiation or incident radiation can given angle. So when number of glass covers are reached, you can multiply with n. So e raised to minus nk delta c divided by cos theta 2. By this one can find out the transmissivity of the glass cover after absorption. So any doubts up to here? Any doubts? So once we take some numericals, we can understand what is the use of these equations. If any doubts are there, you can put a message also in the chat box. Now coming to the next part, here we are going to discuss the reflectivity components in the two mediums. So you can take rho 1 as the here, as I have discussed here, medium 1 and medium 2. So same parameters here we are going to discuss once again. That is, rho is denoted as reflectivities, and reflectivities in which I'm discussing with atmosphere, that is one medium, and one more is the glass medium, that is rho 2. So as considering with the only one glass cover, I can take it as rho 1 atmosphere and reflectivity factor of the component in glass, that is rho 2. So rho 1 I can consider it as, using the atmospheric system and Snell's law, you can write it as sin square theta 2 minus theta 1. Theta 2 and theta 1 is here, like this, divided by sin square of theta 2 plus theta 1. Similarly, if you want to find out the reflectivities in the glass medium or medium 2, I can write it as tan square theta 2 minus theta 1 divided by tan square theta 2 plus theta 1. So using these two equations, one can find out the reflectivity in medium 1 and medium 2. Okay, and using these two values, one can find out the effective reflectivity. It is rho. The effective reflectivity for a given number of mediums. If the mediums are only 2, I can write it as average of rho 1 and rho 2 sum. If I take that average, one can understand what is the reflectivity average value or the effective value. Similarly, if in case the normal incidence radiation is normal to the vertical line, means when the sun is at zenith, the theta 1 will be 0 degrees. See this example. When the theta 1 will be 0, means sun is at zenith. At that time, we can neglect this sign and tan. We can write it using the refractive indexes. So rho 1 will be equal to rho 2 in that condition. And the rho 1 and rho 2 reflectivity values are same. In that condition, I can write it as using refractive indexes only. That is n1 minus n2 by n1 plus n2 whole square. So when the sun is at zenith, so this equation can be used. And one more term, what we are using is this. This is very important. On top I have written tau equal to tau r into tau alpha. So this equation will be helpful for when the transmitted energy through the glass cover is with respect to refraction as well as reflection and absorption. All the three terms are involved. If in that case, I have to multiply the transmissivity due to reflection or refraction and transmissivity due to alpha of the absorption. In that case, the tau will indicate us the effective transmitted energy through the absorber plate. So this tau into alpha, what is indicated here, is nothing but tau r into tau alpha. So in that case, I can multiply IT into tau. So tau is nothing but the multiplication of transmissivity due to refraction or reflection. Tau alpha is the transmissivity due to absorption. And finally, we can also write it as tau into alpha also, because alpha is nothing but the absorptivity. Tau itself is the transmissivity due to reflection or reflection. So that is one of the other terms. Now coming to the transmissivity due to reflection and refraction. Okay, so how to find out this term? due to reflection and refraction separately with the different terms, because here you know all of you how to find out tau alpha in this term due to absorptivity of the glass. But when the reflection and refractions are taking place, in that condition, how to find out this tau r? So this tau r to find out, first we need to understand how the reflection and refractions are going to take place in a glass cover. So here if you consider only one glass cover, okay, one medium as a one medium. So here you can assume the medium of glass cover itself is 1. So whatever insulation is there, the total value 1 if I consider, or 100% if I consider, that radiation after passing through the glass cover, it is going to absorb some energy and also transmit some energy. So in this case, whatever the reflection and refraction is taking place, so refraction procedure if you see, it is going to reduce by some reflectivity value, that is rho 1. So what is rho 1? We have seen in the equation. Rho 1 is sin square theta 2 minus theta 1 divided by sin square theta 2 plus theta 1 is nothing but the reflectivity in the medium 1. So already it is passing through the medium 1 as a glass cover here. So I have considered 1 minus rho 1. And this same phenomena is also taking place with the refraction. Refraction phenomena if you see here, so that depends on the reflectivity of the cover. So that reflectivity of the cover is rho 1. Okay. So same phenomena also taking place after passing through the glass. After passing through the glass, if you see 1 minus rho 1 square, can write it as 1 minus rho 1 square. So all these phenomena due to reflections and refractions taking place infinite number of cycles. Continuously it is taking place between the glass cover and the absorber, or between the two glass covers. So here we have taken only single glass cover. For a single glass cover, how the passage of solar radiations are taking place with reflection and refraction is will be considered. They are not considered absorption. So like this, if you go on adding this, all the parameters which are passed from the glass cover, 1 minus rho 1 square plus rho 1 square into 1 minus rho 1 square. These are the values which are reducing here continuously. So these all values if I sum up and find out the transmissivity due to refraction or reflection, one can write it as the effective formula, that is 1 minus rho 1 divided by 1 plus 2m. So here 1 is nothing but the, after taking common terms. So taking common term as 1 minus rho 1 whole square. If you take the common term, I can write it as 1 minus rho 1 divided by 1 plus in bracket 2m minus 1 bracket close into rho 1. So this is nothing but for n number of glass covers. If it's 1, you can write 2 minus 1. It's 1. So for one glass cover, it will be 1 into rho 1. That is 1 plus rho 1. So for one glass cover, I can write it as 1 minus rho 1 divided by 1 plus rho 1. Similarly, tau R2. Tau R2 for the second medium. If the absorber plate of the glass cover, second glass cover, then we can write with one glass cover 1 minus rho 1 rho 2 divided by 1 plus rho 2. If it is m number of glass covers, 2, 3, 4, 5, 6, like this, if I increase number of glass covers, then we can include this formula, that is the common formula 1 minus rho 1 divided by 1 plus 2m minus 1 into rho 1 for the reflectivity and refraction for the one medium. If it is second medium, below this, if I consider second medium like glass cover or absorber plate, I can write it as 1 minus rho 2 divided by 1 plus 2m minus 1 into rho 2. Okay. Now we'll discuss the absorptivity. So until now we understood how the reflection and refraction phenomenon takes place in the glass covers. Also we have to see how this absorptivity alpha takes place in the system. Okay. So here we can define this product of the absorptivity or transmissivity product as the ratio of the flux absorbed, flux in the sense solar radiation per unit area. It's a flux absorbed in the absorber plate to the flux incident on the cover plate. So cover plate solar incident will be high compared to the solar radiations absorbed by the absorber plate, because absorber plate receiving will be with a lesser area, and the energy incident on the absorber plate will be a little bit high. So this ratio, if you consider, I can write it as tau alpha as total incident radiation, okay, which is passing on the absorber plate will be tau alpha, and the total flux incident on the cover plate. Here, in this below phenomena to see, we have considered alpha also. So solar radiation is falling on the cover plate, the entire cover system. We can assume it as one system. So here, this first line, we can assume n number of glass covers. It may be one, or it may be two, or it may be four, like that. Cover system. Okay. At the bottom, if you see, this is the absorber plate. And on the absorber plate, what is the solar radiation received? Is the effective solar radiation received. Okay. So that is received by passing through glass cover. And through this glass cover, we have transmission due to reflection or refraction, that is tau, and alpha is nothing but the absorbed radiation. Some radiation is absorbed by the cover system also. And effective radiation in one cycle or one phenomenon will be tau into alpha. Or you can also multiply with incident radiation, as we discussed in this sketch. Total radiation into tau into alpha. Same thing is considered here, tau alpha. And after this one cycle, in next cycle what will happen? Some energy will be reflected back. Some short wave wavelengths will be lost to the atmosphere, and long wavelengths will be reflected back. So what is reflected back is nothing but tau into 1 minus alpha into rho d. So here rho d indicates the diffuse radiation, because all the radiations which are reflected back are the diffuse radiations. The radiations which are directly passing from the sun are taken as beam radiations, IT, or total radiations. So to indicate that it is diffuse radiation from the glass itself, we are writing it as rho d, reflectivity index due to diffuse radiation. So effectively, if you see the reflected back radiations, it is having tau into 1 minus alpha, because alpha is absorbed in the alpha is absorbed by the glass cover. 1 minus alpha is the total absorbed energy by the absorber tube. After that, some reflection is taking place. Then the diffuse radiations is multiplied here with the reflectivity, diffuse radiations, or reflective diffuse radiations are multiplied here back to the system. That is denoted by rho d. Okay. So rho d is what? Diffuse reflectivity of the cover system. So from the cover system, this radiation will be again received back to the absorber plate. Now if you multiply tau alpha, because alpha is again absorbed radiations in the glass. After absorption to the glass here, this small arrow mark is nothing but alpha, which is absorbed by the glass. Then it is reflected back. Then I can take this tau transmission, or due to refraction or reflection is taking place. Then 1 minus alpha from the glass cover is also multiplied, and rho d is the diffuse reflectivity. So similar case, if you take for the next cycle infinite number of times, it will be square. So like this, on the absorber plate, what energy is received, that we are focusing. So to write everything, you take the sum of tau alpha plus tau alpha into bracket 1 minus alpha into rho d plus tau alpha into bracket 1 minus alpha square rho d square, like this for an infinite number of terms. I can take tau alpha as a common term. That's why you can write the ratio of this flux absorbed in the absorber plate to the flux incidence on the cover plate. If you take ratio, I can write tau alpha equal to tau alpha divided by tau alpha is nothing but the actual radiation received on the absorber plate by the sun, or through passing through one of the glass cover system or cover system, we receive tau alpha, to that of total radiation received after multiple reflections, reflections and refractions, total radiation received. So that much energy will be reduced. So we can write 1 minus alpha into rho d is the effective term. Okay. I think we'll stop theory here. we'll take some of the numericals to understand what is the importance of these equations. All these equations, how it will help to find out this reflectivity, reflection, absorptivity, and to find the different parameters of the effectiveness of the glass cover system. And also it is predicted by the claim that up to 60-degree incident radiations here. Incident radiation theta 1, if you see in this sketch, up to 60-degree, there will be no loss of energy, very less loss of energy, or the efficiency of the black plate flood will be good. But once this incident beam radiations is crossing from 0 to 60-degree and beyond 60-degree, if you see, say for example 70-degree or 80-degree or 90-degree incident beam radiation, the energy issued on the absorber plate of this refracted beam radiations will be with the lower energy, or the efficiency of this black-white plate will be less. So that we'll see in the numericals. I'll take one numerical. Yes. So in this numerical, you can see for a glass cover system, estimate transmissivity due to reflectivity, that is rho, transmissivity due to absorption tau alpha, and effective tau. So tau is multiplication of tau r into tau alpha. The total tau you can find out for the following data. So what is data given here? Angle of incidence. Angle of incidence means theta 1. You can consider the Snell's law. So theta 1 is given 45 degree in the atmosphere. Solar radiations are falling incident on the glass cover at 45 degree to the normal line or the vertical line. 45 degree theta 1 is given. Also, theta 1 indicates the reflection. Let's see here. Reflection is also theta 1. Here. Incident angle is theta 1. Reflected radiation is also theta 1. So both are 45 degrees given in the top. The next given is number of covers. So number of glass covers is 2. So where m or n value is required, that they have given 2. Thickness of each cover. So thickness value is given 4 mm. So where this thickness value is required, I told you it is in the Claims formula. That is K into delta C. Delta C is the thickness of the glass cover. It is given in mm. We will take it in meters because extinction coefficient is also given in meters. So 4 mm you convert it into meter. 4 into 10 to the minus 3 meters. Next given is refractive index of the glass. So refractive index of the glass is N2. Okay. So from this N1 can be found. Refractive index of glass relative to air is 1.5. Okay. So that value is given. So that value is nothing but N2 by N1. Refractive index of glass N2 relative to air. Air medium is N1. So N2 by N1 is 1.5. Then extinction factor K is given for the glass 15 per meter. Now coming to the first thing is we must know the reflectivity because we want to find out transmissivity due to reflection or reflectivity index rho. To find that rho value, one should know this theta 1 and theta 2. If you find that theta 1 and theta 1 is already given 45 degree. Theta 2 we can find out the Snell's law. So Snell's law, what it is? Sin theta 1 by sin theta 2 is equal to N2 by N1. Or I can write it as N1 into sin theta 1 equal to N2 into sin theta 2. So by this I can write it as sin theta 1 divided by sin theta 2 equal to 1.5 is the refractive index. Now using this relation, one can find out theta 2. As theta 1 is given, N2 by N1 is given, I can find out theta 2 equal to sin inverse of sin of 45 divided by 1.5. So that will give us 27.72 degrees. So theta 2 is nothing but refracted radiation after passing through the glass. That value is theta 2. Now rho 1, as I told you, rho 1 is given by sin square theta 2 minus theta 1 divided by sin square theta 2 plus theta 2. So using these values, I can find out 0.097 is the reflective component after the light passes through one glass core or first medium. Please check these values whether these values are correct. You can comment in the chat box. Or if the values are correct, you can continue the class. Sanket, am I audible?
Yes, sir. Sir, but I don't have calci, sir.
Yes?
I don't have calci, sir.
Okay, okay. Online also don't have. Okay, I
I
hope.
left in Belgaum only, sir. I forgot to bring.
Okay. So now we have found out the reflectivity index of medium 1. Now for medium 2, as I have told you, tan square theta 2 minus theta 1 divided by tan square theta 2 plus theta 1. In that we substitute this theta 1 and theta 2 values to get this reflectivity index. Okay, reflectivity index in the medium 2 after passing through glass cover 2. That value is coming around 0.009. So using this rho 1 and rho 2, now we can find out transmissivity or uh, transmissivity due to reflection or reflective component by 1 minus rho 1 divided by 1 plus 2 n minus 1 into rho 1. Or earlier we discussed 2 into m minus 1. So m or n is nothing but number of glass covers. In this problem, they have given number of glass covers as 2. Only thing is we have to substitute rho 1 and n values. Rho 1 is how much we got? 0.097 and n value, number of glass covers is 2. So 1 minus 0.097 divided by 1 plus 2 into n is 2 into 2, 4 minus 1 is 3. So 3 into rho 1, which is 0.097. So transmissivity due to reflection is 0.699. Similarly, in second medium, or second cover, we can go for same formula with rho 2 values. I can get 0.965. So using now or taking the average of these two values, one can find out the transmissivity due to reflectivity index or the due to reflection. The transmissivity due to reflection, I can find it as average of rho 1 or tau rho 1 and tau rho 2 will give us 0.832. So see here, this is the reduction. What these values indicates is, if you say for example 100% solar radiation is falling on the flat plate collector, after passing through these two glass covers, the reduction in the transmission value will be 0.83. Okay, so out of this 100%, say for example 100 minus 83.2, if you take so much value of solar radiation will be reduced. That's the meaning. Similarly for absorption, using this claims or Boger's law, one can write it as for transmissivity or transmission of energy after absorption. This is after reflection, tau rho. After absorption, I can write it as tau alpha. Okay, so here in the entire problem, they are not talking about the refraction, only reflection and the absorption they are asking. They are finding only that much. So absorption of this solar radiation can be given by or after absorption of the glass covers, number of glass covers n, how much energy is transmitted. That indicated by e raised to or exponential of minus n into k delta divided by cos theta 2. So why they have taken cos theta 2? Because there some incident angle is given. Also some refracted or yes, refracted angle is also found out. So due to that, we have taken cos theta 2. So that is given by e raised to minus number of glass covers 2 extinction factor 15 per meter. Delta C is the glass cover thickness. The glass cover thickness is how much each cover? 4 mm. So already 2 is multiplied. You need to take 2 times this 4 value. 4 is in mm. I have taken converted into meters. 4 into 10 to minus 3. divided by theta 2 is 27.72 degrees. That's found out earlier. So that is substituted here. Now one can find out tau alpha is nothing but alpha only. Energy transmitted after glass cover absorption of the energy. Okay, so that energy, how much it is lost is 0.873. Now if you multiply tau alpha and tau rho, I will get effective transmission of energy. Tau rho is how much? We got 0.832. Tau alpha is 0.87. Okay, so that is 0.726. This much energy is transmitted, means 72%, almost 72.6% of energy is transmitted on the absorbing plate after passing through two glass covers. The tau rho will indicate like tau r here. The main formula what I told now, this formula. First formula you see here, tau equal to tau r into tau alpha. Same thing we have used. Whether this tau is due to both reflection and reflection. What they are telling? They are telling that tau is due to reflectivity. So due to reflectivity, what is the energy transmitted that we are finding? That's why we are writing this equation as tau rho into tau r. To consider reflection also, then the equation will be tau r. This r is due to reflection as well as reflection, both. Okay. So we'll take one more problem. Say in the same equation, we have to just substitute given values. Okay, we'll take one more problem. This will give us more light towards this topic, what we are discussing. See now, plot the variation of tau r, tau alpha, and tau. Now in this problem, they are not asked tau rho. Means now they are talking about both the phenomena. All three phenomena they are talking about. Tau r is the transmissivity after reflection and refraction phenomena. Tau alpha is after absorption phenomena through the glass covers. Then we need to find out total transmissivity of the transmissivity and absorptivity product tau. Tau we need to find out. Okay. Then we have to plot the variations of these all three parameters with the angle of incidence. So I think angle of incidence we can take on x-axis, and this all three variables tau r, tau alpha, and tau on the y-axis, and we can plot the graph. So for which we have to plot the graph. So that bracket is material is glass. Okay, number of covers are two glass covers are given. Refractive index of the glass relative to air. Again same thing. N2 by N1. N2 is the glass, second medium. First medium is air because solar radiations are passing through the air and passing through glass. N2 by N1 is given 1.52. Extinction coefficient of glass is also same given 15 per meter. So these all things are given, and also angle of incidence they are telling that it is 15 degrees. So using all these details, now we need to find out what is tau r, what is tau alpha, absorption, and tau, effective transmissivity. So already we have gone through the process, same process you have to follow to find these parameters. So we come to the finding the theta 2 by Snell's law. Theta 2 or reflected radiation angle is coming around the 9.80 degree. Theta, rho 1 reflectivity. Because in the question you can see tau r is due to reflection as well as refraction, both. That's why we need to find out rho 1. So rho 1 value is coming around 0.047. Rho 2 using tan formula is coming around 0.039. So using these two, one can find out tau r1 and tau 1. Okay, so tau r1 is what? 1 minus rho 1 divided by 1 plus 2m minus 1 into rho 1. So rho 1 value is 0.047. M, number of glass covers, 2. 2 into m is 4 minus 1 is 3. 3 into 0.047. So tau r1 value will be 0.835. Similarly, tau r2 using same formula, 2 number of covers and 2 to substitute here in this formula. 1 minus rho 2 divided by 1 plus 2n, 2 into 2, 4 minus 1, 3 into rho 2. Rho 2 is the second medium, last medium, 0.039. Using that value, I will get tau R2 as 0.860. So you have to take average of these. So once you take the average of these two, I'll get tau R value. Because they're asking the tau R value should be plotted on the graph later. Value is 0.848. You take the average of these two. Okay. So similarly, using Clay's or Vogel's law, it is tau alpha, transmissivity of the energy after absorption through the mediums, I as e raised to minus n number of glass covers into k. K is extinction coefficient or Clay's constant, is also given 15 per meter into thickness of the glass covers. For mm they have given thickness 4 into 10 to minus 3 meters divided by cos theta 2. Theta 2 is 9.84 meters. So tau alpha I can get 0.885. The effective tau is for 15 degrees. Now see in the question, we are not given incidence angle itself. That's why in the solution, we have assumed theta 1 is 15 degree and tau we have found out 0.750. Next thing what we have to do is theta 1 you have to assume 20 degrees, 30 degrees like this, you have to go on again. Then what you can do is for incidence angles, 15 degrees, 20 degrees, 30 degrees like that, you can plot the values of tau 1, tau alpha, tau found out by these formulas. Okay, it's a recurring process. Now once you plot this graph, see here, for incidence angle 15 degrees. So I think this is the 15 degrees. 0 degree and 30 degree in between. I can assume this is 15 degrees incidence angle. For that, tau value. See here, at the top, tau alpha is shown, at the in between, tau r is shown, at the bottom, tau is shown. So what is the value for 15 degrees? For 15 degrees, tau is 0.750. That is shown here. Tau value is 0.750. Here in between 0.6 and 0.8 and 0.75. Almost here we are shown. Tau r is how much? Tau r is 0.848. So above 0.84. Below to 0.85, therefore 0.84 here, tau r value. Tau alpha is how much? Tau alpha is 0.88, more than tau r. So above tau r, tau alpha value. So above tau r value 0.88. So here we are showing tau alpha, here to 0.9. Okay, this is for one value. I can draw here one line. This is for 15 degrees. 0 degree, 30 degree, 60 degree. Like this, you will go on finding all the values for incident radiation, and you have taken up to 90 degree because we talk about sunrise 90 degree to 0 degrees. Afternoon, you can take from 0 degree to sunset 90 degrees. That's why we have taken 0 to 90 degrees. So in problems, you can take 15 to 90 degrees, or you can take only 30, 60, and 90 degrees, and you can plot this curve. So once you get at least 2 or 3 values, you can plot it curve or you can draw a curve for tau, tau r, and tau. Okay, in the problem, you have taken 15 degrees. In later stage, to plot this graph, you can take different angles 30 degree, 45 degrees, 60 degree, 20 degrees, 90 degree, 80 degree. Problem itself has 10 number of problems. 9 test for exams. Okay. Okay, what's the time? 56. Okay, and the last one more problem I'll take and I'll solve the class. Okay. The last problem in this topic, because this topic will cover while solving this problem. A glass cover of 3 mm thickness, so delta C is given 3 mm, take it as 3 into 10 to the minus 3 thickness, is provided in a solar collector. The transmissivity of the glass when reflectivity is considered 0. So when you consider reflectivity at tau r value 0, means it is tau alpha. So tau alpha given as 0.95 in this problem. 0.95 is the tau alpha, and transmissivity when absorptivity alpha is 0. When alpha is 0, you can consider this as tau r. Tau r is 0.76. So in this book, they have taken tau T2 or T1 whatever, but as per concept, when the reflectivity is 0, I can keep it as absorptivity, tau alpha as 0.95. If the absorptivity is given and reflectivity is, sorry, absorptivity is considered 0, then I can keep it as tau r. So tau r is 0.76. So when tau r is tau alpha both are given, I can multiply both and I can find out total transmissivity to the glass. That value is 0.7, 1.1. Okay. Next is the reflectivity of the glass is. So reflectivity is given, means it is rho value. As per our discussion, it is rho reflectivity. In this book, we have considered it as R. Only change in some parameters, but the value we can understand. The reflectivity of the glass, both the glass is 0.22. So rho I can consider it as 0.22. So find out the net percentage energy absorbed. Clearly read the sentence. What we have to find out. Find out the net percentage energy absorbed by the collector plate, means absorber plate. How much energy is absorbed in percentage, not in value. How much energy is absorbed in percentage, whose absorptivity is 0.09. Now this is absorption or absorptivity of the plate. That plate is given 0.09. Now going back to the energy absorbed by the collector. See what I told. Effective radiation falling on the absorber plate is this phenomenon. Here, this is the plate, this is the glass cover system. What is the equation we have to use for transmitting and absorbing product or the percentage of energy absorbed by the plate? You can find by using this formula. Tau into alpha divided by, or you can take product, tau alpha product divided by 1 minus into bracket 1 minus alpha, the absorptivity of the plate, into bracket rho d. Rho d is diffusive reflectivity. So reflectivity value is also 1. What is that 1 value? Reflectivity. Reflectivity is given here 0.2. So tau, sorry, total tau is 0.722. Alpha of the absorber plate 0.095. So it should be actually 0.95. I'll take this one. Tau into alpha. Tau into alpha is 0.95 into bracket 1 divided by, I think here either absorptivity should be 0.095, should be substituted here in both the alpha values, or else you take this question itself as 0.95 for absorption period as well as for the glass cover 0.95. Okay, so that is a correction what you have to make. Or take one more problem, substitute this 0.95 as 0.095, make it a new problem. Into reflectivity index 0.2 is given. Finally, we can get the answer as 0.694. So in percentage, if I write the amount of energy falling on the absorber plate, of the absorber plate, how much energy it can absorb from the solar radiation, 69.4. Okay, so there is a printing mistake in this entire solution. So you check with this value as well as 0.95 values and write it in percentage. I hope the time is up. Any doubts in this class, you can put it in the chat box or you can ask in the next class so that you can clear all these doubts and move to the next topic. Okay? Thank you.
Sir,
Okay.
yes, sir.
Did you understood some concepts today?
Yes, sir. Fully understood, sir.
Okay. So same formula will be same. Sometimes they will ask the answers in numerical, or they may ask the answer in the percentage student, or they may ask to substitute different angles and plot a graph.
So when is IS, sir?
Still, it is not clear because 15, 16, 17 was decided earlier. Now it is postponed.
When, sir?
So, it is postponed now. Still, it is not decided.
It will be offline or online, sir?
Until now, they have told online. So once the dates are clear, you can come to the college. Okay.